So moving ahead now, today we are going to review because all the sorting and the searching techniques, most of them you have studied in the data structures course. So we are going to have some fast review of the various topics and discuss the time complexity of all these algorithms, right? So during the practice and during the learning of the asymptotic analysis, we have seen how to compute the time complexity of the various relations which are given to us, various recurrence relations which are given to us. So now let us understand the time complexity of the various searching as well as the sorting algorithms. So in the module 1, the highlighted part we are starting today, that is empirical analysis of sorting and searching algorithms, merge sort, quick sort, heap sort, radix sort, binary search and median search. Okay, so we start with the analysis of the searching techniques and analyze the time complexity. So we'll start with the linear search, binary search, median search, then followed by the various algorithms which are used for sorting and their time complexity analysis. So what are the searching techniques you have studied? So we have, you people have already studied the linear search as well as the binary search. Median search you have studied? Yes? Have you studied the median search?
Yes, ma'am.
Okay. So you already know that in the linear search, what do we do? We have, this is the basic searching technique that we use. This is popularly known as the linear search. As we make comparisons with each and every element, as we move ahead, we compare the elements which are there in the array with the element that we are searching for, because we want to know what is the position of this particular element X in the given array. So when we are searching for the element, you can say we have two cases. One is either the element is present or it is not present. If it is present, we will definitely get the index of that particular position where that element has been found. And if it is not present, that means we are going to show some message that element is not available in the list. So this is the code for the linear search algorithm. This is the iterative implementation code. So here you can say we start with the main method. In the main, we have declared one array of size 5. Then we need to have some element which we want to find in this particular array. So let's say it is given as x. Then we take n as the size of the array. And then you see we have written one function that is called as linear search, and we call this function and we are passing the array, the size of the array and the element that we want to find into this. And now we see the code for this particular linear search function. Here you can see we start with the declaration of a variable and then we have a for loop. In the for loop, what we are doing, the simple comparison of the element that we are trying to find with all the elements of the array one by one using the index value I. So if the array is found, the element we are looking for, it is found in the array, then what do? We return I. I indicates the index position or the position where this element has been found. If it is not found in the array, then we return the value that is -1. So -1 indicates that the element is not present in the array. So we come back to the main function and then we see if result is equal to -1, -1 indicates element is not present. So appropriate message is been shown to the user, and otherwise, that means otherwise it is going to return I. I represents the position of the element in the array. So we are printing that value by using the cout method over here. The element is present at index, that gives us the value of the index position where the element has been found. So from this particular code, what do we see? How to analyze the time complexity of this particular array. So how many loops are there and what are the various operations which are being done in this particular code. So we know where after studying about the asymptotic analysis, that we look for the three cases when we compute the time complexity of the algorithm. One is the best case, another is worst case, and third one is the average case. So in the best case, what is the minimum number of comparisons that can be done for n items? That is equal to 1. That means the best case is the element that we are searching for, that is, it is available as the first element to be examined. So in the array, if it is the first element, so we only require one comparison and the element is found. So that means that is the minimum time the algorithm will take in best case. In the worst case, it is the maximum number of comparisons. So the maximum time that you can say the program may take to execute is, so in that case we have two cases. One is x is the last element examined. That means if the size of the array is 10, then the element you are searching for is the 10th element in that particular array, but we are not aware, right? So we have to compare that one by one only, so we will have to do the 10 comparisons. And then second case is element is not in the list, and this case also relates to the case one only, because for depicting this particular message that the element is not there in the list, we will have to do all the comparisons. So we will have to compare the element to be found with all the elements in the array. That means we will have to search the complete array. So the complexity of the worst case complexity of the linear search algorithm, it becomes O of n. So here you can say the best case, the worst case, and then we talk about the average case. So in the average case, how many comparisons will be required? That depends the order of the elements in the list. It may be in what order we are getting the list, we are not aware at all. Then the probability that x is in the list at all, that means again, so what is the probability of getting the element in that particular list? So let us assume that the x appears in the array and it is equally likely at any position. That means it can be at any position in that particular array and its probability is given as 1 by n. So the probability of, so we on the basis of this probability we compute the time complexity, and this is given using the relation t of n is equal to 1 into 1 by n plus 2 into 2 1 by n plus 3 into 3 1 by n up to n into 1 by n, and this is equal to 1 plus 2 plus 3 up to n into 1 by n, and this can be represented as n into 1 n plus 1 by 2 n into 1 by n, and which is equal to, see, from this relation we can derive 1 by n is the constant we can ignore. Then we are left with n plus 1. 1 is again the constant, again we can ignore. So the final time complexity, even the average time complexity of the linear search algorithm is of the order of O n. Any doubts in this? Yes, please. Any doubts in the understanding of the time complexity of the linear search?
No, ma'am.
Okay.
No, ma'am.
Okay. So let next move on to the binary search algorithm. We know about the binary search algorithm. It is based on the divide and conquer strategy. So it works, but there is a prerequisite that binary search can be applied only when the array is sorted. But the linear search can be applied on any type of array. There is no prerequisite of that. So that means if you are having an array which is having unsorted data, you have to apply the linear search, and if it is sorted data, that means we have to apply the binary search. But what can be the other options for searching the data when we are having the can we have some better algorithms as compared to the linear search when the data is not sorted? So let us first discuss the binary search algorithm. If you have a sorted array, then your binary search will perform better than the linear search. So in the binary search, what do? We start the array searching from mid of the array and check whether the element is at the mid position or not. If the element is not at the mid position, we divide the array into two parts. One is the left subarray and the right subarray. If the mid position, if our element is greater than the mid, then it will lie on the right hand side. If it is less than the mid, then it will lie on the left hand side, because we are saying our data is arranged in the ascending order. So because in the ascending order, the data moves from the minimum value to the maximum value. So on the left hand side, we say we have the minimum value. On the right hand side, we have the maximum value. So from the mid, we compare whether the value, the given value that we want to find out in that particular array, whether it is less than or greater than that. Accordingly, we will start the size of the array is reduced to half after every iteration. So we reduce the process until the element is found or the process is end. So let us see the iterative code of the binary search. Here you can see the function we have created, that is int binary search. So input, again, because it is a searching algorithm, we have three things that we are giving as input. One is the array in which the elements are there. Then we have r, you can say this is the size of the array. And then we have x, x is the element that we are searching for. So now while 1 is less than equal to r, that means we are saying we are iterating to the through the complete array, right? So while iterating through the complete array starting from 1, int mid is equal to 1 plus r minus 1 by 2. So we are trying to find out the mid value of this particular array. So then we compare, because x is the element that we are searching for. So we search and see if a mid is equal to x. A mid is the value, some index value that we will be getting, because that is the let us say the size of the array is 7. So the middle element will be, what will be the middle element if the size of the array is 7? Aditri, Aditri,
Yes, yes, ma'am.
what is the middle value if the size of the array is 7?
Uh, ma'am, 3.
मिडल एलिमेंट 3 होगा, साइज ऑफ द एरे इज 7.
Ma'am, yes, ma'am. Middle,
ओके, जीरो
middle
से स्टार्ट कर रहे हो गया,
index.
जीरो से स्टार्ट कर रहे हो इंडेक्स. ठीक है,
Yes, ma'am.
ठीक है, right? So what do we do when we write a of 3? That means the value that is at the index position 3, that is equal to x or not. If it is equal to x, we return the mid. That means we have found the position of the element we are searching for. Otherwise, what do we do if it is not equal to? Then we compare if a of mid is less than x. If a of mid is less than x, right? So that means x is greater than a of mid. If x is greater than a of mid, that means our data, the point we are looking for, that lies on the right hand side, right? So what do? We make L is equal to mid plus 1. That means this, you can say, the lower value. So the lower end is equal to mid plus 1. So the you can say we have divided the array into half, and now we will be searching from L to the R. R is basically the end of the array, the size of the array. So we are searching, now we are going to, so that means now it has reduced the array into sub array, that is n by 2, right? Then if the last case that is left is if a of mid is greater than x. If a of mid is greater than x, that means the value, our data that we are searching for, that lies on the left hand side. If it lies on the left hand side, then we ignore the right. How do we ignore the right? By taking moving the, you can say, the length of the array to half, that is r is equal to mid minus 1. So that means our array is reduced to half between L and new r. New r is the new length of the array, that is divided by 2. So otherwise, if we are able, if we reach the here, that means if we are not, after iterating through the complete process, we are not able to get the element, we return minus 1. Minus 1 indicates that the element is not present in this particular array. So the recursive code of this binary search that you can write is, if left is equal to right, if x is equal to a of left, return left. That means when we are comparing, the both left and right are same. So that means we have reached to the middle of the element. If middle of the element is equal to the x, that the element that we are searching for, so that means we return left. Any element we can return. Else we return minus 1. Right? Then if the element is not found, the minus 1 is returned. This case will not be satisfied. So we reach here, mid is equal to left plus right by 2. So left and right are basically the ends of the array, the sub-array that we are computing. So if x is equal to a, mid, return mid. If x is less than a of mid, these are the three conditions that we have seen previously also. But there is a small change when we have to write the recursive code for the binary search. If x of a is less than mid, return binary search a x a left mid minus 1. And if x of a is greater than this, then return binary search with a mid plus 1 right. That means here we have changed the you can say if the value of x is less than mid, that means our element lies on the left hand side if it is there, right? If it means there are chances that it may be there on the left hand side. If the value of x is greater than a of mid, there are chances that it will be on the right hand side. So accordingly we are you can say using by changing the values of the left and the mid, we are reducing the size of the array. So now the array is reduced to half, and iteratively we keep on repeating this process until we have searched all the elements, or this process is complete, or we have found the element. So now, when we have to compute the time complexity of the binary search, we have studied about the various methods, the recurrence. We have studied how to compute the time complexity of the recurrence relations. So what kind of recurrence relation that we have seen over here is that we visit one element, then search either the left or the right subarray. That means the size of the array is divided into half. Always array is divided into two parts. The recurrence relation of binary search is T of n is equal to Tn by 2 plus 1. So if n is equal to n by 2, then we are able to get Tn by 2 is equal to n by 4 plus 1. So similarly, if we keep on iterating this process and we get that, and we apply the iterative method, so we get Tn is equal to Tn by 4 plus 1 plus 1. That means Tn by 4 plus 2. If you can recall, we have already done this example of the binary search during the asymptotic analysis. And when we do it for to keep on iterating this process, we are able to find one pattern. That pattern, as we show you, so this pattern becomes T of n is equal to Tn by 2 power k, because over here this is, you can say, when we are writing Tn is equal to Tn by 2, you can say this is 2 power 1, then 2 power 2, then 2 power 3, because it becomes 2 by n by 4. N by 4 is equal to 2 power 2, n by 8 is equal to 2 power 3. And on the other and also that constant value is also equal to the power of 2. So here you can see, if we generalize this, we can write it Tn is equal to T n by 2 power k plus k, where there is only one element, then only in that case T of 1 is equal to 1. So comparing this, so if we say when there is only one element, T of 1 is equal to 1, then n by 2 power k is equal to 1, we can write. So we take the log on both the sides. When we take log on both the sides, we are able to get k is equal to log of n. So we put this value and we say that T of n is equal to T of 1 plus log base 2 of n, and this is equal to O log of n. That means the time complexity of the binary search algorithm is of the order of O log of n. That is also we have already discussed. So which is less than the you can say which is less than the other binary search algorithms. But if there is a prerequisite, we can apply this algorithm only when the array is already sorted. If the array is not sorted, then what do we do? Can we have some better efficient algorithm as compared to linear search for finding out the element, or you can say for searching an element from the array? Because you can say the size, as the size of the array increases, the time complexity of the linear search algorithms becomes very high. Like for a size of 100, you can say the time complexity of, again, it is of the order of n. So you can say if it is 1 million, size of the array is 1 million, order of n becomes very high. So in order to solve such kind of problems, can we have some time searching algorithm which is of the order of log n, as we have done in the binary search? So there is another algorithm, good algorithm, which is used for finding the element, and this will of the order of n log n time in an average or the best case. And this algorithm can be applied on the unsorted array also. So there is so sometimes the your median search is defined as a you can say, what do we do in the median search algorithm? We find out the middle. See, In the linear search, we are not finding any element, but in the binary search, we are making our comparison with the middle value. We find out the central value because there we are following the divide and conquer strategy. But in case of median search, we are finding the median value of that particular array. So the median of a list of n values is found by sorting the input array in increasing order. So that means first of all we'll have to sort, apply some sorting algorithm, and then find out the median value. Now taking the middle value, this will take all n log n time in an average case. Like here we see one example. If we have 5 elements in the array, its median is 19. So the first definition is easy to grasp, this particular definition that we are talking about, that you sort the array. But again, taking the central value, and for that sake we have to sort the array, this is not considered to be the appropriate concept. So in order to solve this particular problem, we go for the median search, which is, and this median search is the algorithm which is used for finding the kth smallest or the largest element in the given set of values. If you are asked some question there, you are asked that you find out the second smallest value from the array, or the third largest value from the element in third largest element in the array, or the fourth smallest element in the array. For finding out such kind of elements, we use the median search. So you need not think about something else. You directly apply the median search algorithm, and you will be able to find out the kth smallest or the largest element from that particular array. So now the median search algorithm, what do we do? So first of all, you find out the median as well as the kth smallest element, because I said, so you can apply this algorithm for any of these purposes. So what do we have as the input? We have a S, that is a list of numerical values. K is the rank of the kth smallest element in the list, that is S. So what is the procedure? Here you see the function, and then we will see one example with the help of which it will become easy for you to understand the things. So here we see, if S is equal to 1, then we return single element in the S. If else, choose an element A randomly from the S. That means if there is single element, of course, so then we can return that single element because there is nothing else to do. But if there are large number of elements in the S, what do? We choose some random element first, right? From the size of the list. If there are 10 elements, we have to find out the random number from the, you can say, in the range 0 to 9 only, right? So after taking up that that number randomly, let us we divide the sequence, the array sequence that we are given, into three parts, right? So one is S1, another is S2, another is S3, and these are the subsequences we have derived from the S, which are equal to, less than, and greater than A. Let us say we have 10 elements in the array, and the random number generated is 6, right? So we will have three subsequences from the S. One subsequence is equal to 6 only. That means that will have only the element A that we have randomly generated. Then the second one will be less than 6. That means all the elements, let us say 1, 2, 3, 4, 5, all these elements are less than 6. And then another sequence which has all the elements greater than 6, let us say 7, 8, 9, 10. I'm taking direct numbers so that it becomes easy, but I will be taking an array, an example where I have taken the random numbers. Now if the size of the, see, now here we are talking about, just focus on this, we are only focusing on the size of the sequence. So if the size of the sequence S1 is greater than equal to K, what is K? That is the rank that we are searching for. If it is greater than this rank that we are searching for, then we return, select K of S1, right? This is the first condition, right? Because we are calling that particular function and passing the rank, and then passing only that particular sequence only, right? That subsequence of the array. If the rank of S1 plus S2 is greater than equal to K, right? Then we will be returning that random variable that we have generated, that is A. That means this is the element that we are searching for. And otherwise, what do? We return, and we call that particular function So you can see it is a recursive function. So k minus k was the rank minus the rank of S1 minus S2 comma S3. So this is how we are calling. So that means whatever value that comes out, that becomes the kth element, and S3 is the subsequence from where we will be searching, and this process will keep on repeating. So this is how, and when it has found, when the rank of when the size of the array is 1, so the element that we return, that is basically the kth rank of the you can say it is the kth smallest element in the array, or the element that we are searching for. So let us do one example and then we understand. So let us see let us say we have these elements. So 7, 10, 4, 3, 20, 15, 8, 12. The size of this is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 elements. So now we have randomly generated an element, and that comes out to be 10, right? So generated some index value. On the basis of that, we have picked one element that comes out to be 10. So now the algorithm says that we have to divide on the basis of this value of 10 that we have generated randomly. We have to divide the array, that the given array, into 3 subsequences: S1, S2, and S3. S1 is having the subsequence which is less than 10. So from the array we see the number of elements which are less than the value 10. So 7, 4, 3, 8, 6, all these values are less than 10. Then the second subsequence S2 is equal to the random element that we have generated, A, that is equal to 10. So the third subsequence has all the elements which are greater than 10. So 20, 15, 12. So here you can see the size of all the subsequences are different. So we are only focusing on the number of, not on the number of elements. We are focusing on the values of the array which are greater than the randomly generated value. Now the length of S1. Now we apply the conditions. Now we have 3 subsequences. So now we start checking to find out the kth smallest or the largest element. Now the length of S1 is greater than equal to k. So here we are searching. See, in the beginning, what we are doing, the find the k is equal to fourth median. So we are looking for the fourth median value, the fourth smallest value, or the fourth largest value, we can say, right? So now for finding out that particular value, what do? We first check the first condition. The length of S1 is greater than equal to k. What is S1? So it has 5 values. Its value is greater than the length of k is greater than equal to the median value, that is k. Yes, this condition is true. So what do? We select 4 comma S1. As you can see, the 4 is the k and S1 is the subsequence. Now we check in this particular subsequence only. See over here. So now we are checking into this subsequence only, and we check in the array S1 is equal to 7, 4, 3, 8, 6. Now we again randomly generate one number and it comes out to be 3. We again repeat the process. We divide the subsequent given array. Now the array we have is only of the size 5, and its element are 7, 4, 3, and 8, 3, 8, 6. And then on the basis of this a random value, we have what we have. See, here you can see we have no value which is less than 3. So the size in the subsequence S11 we have nothing, right? So in the S12 we have the element 3 only, the element itself, and in the S13 we have 7, 4, 8, 6, all the values which are greater than 3. Now when we check the conditions, our first value, see, the first condition is length of S1 is greater than k. The length of S1 is not greater than, this condition is not satisfied. Then the length of S1, you can see the rule. So in the first condition, length of S1 is greater than equal to k. No, because in the S1 there is nothing. So, and the value of k is 4, which is less than that. So this condition is not satisfied. If S1 plus S2 is greater than equal to k, no, because in S1 we have nothing. In S12 we have only one element. So the length of this, even if we add, this is less than that. So that means the first and the second condition fail. So we apply the third condition. Third condition says call this particular function again, and what do we have to, what is the new value of k? That comes out to be k minus length of this minus length of this, and S3. So S3 is this particular array, S13, and this comes out to be, because the value of k, that is 4, it was initially 4, so it becomes 4 minus 1 is equal to 3, because 4 minus S12. So its value is 0, S12 is 1, so it becomes 4 minus 1 is 3, and then we are passing the third sequence subsequence, that is 7486. Now again we generate a random number. Here you can see, now we had seen the value of k was equal to 3. So we again randomly generate a number, and let's say this comes out to be 7. So in the first subsequence, that is S, see these numbers you see S131 we have taken in order to understand the steps that we are taking. From the first level we had taken the S1, from the second level we had taken the 3, and now we are moving on to next. So the third level, you can say it is the third iteration, third step we are taking. So S13 is 7486, randomly generated number is we have chosen is a is equal to 7. So the first sequence has all numbers less than 4, which comes out to be 46. S132 is equal to the number itself, and S133 is the numbers which are greater than 7, which is only equal to 8. So now here the condition 1 fails because k is equal to 3, and S1, the size of S1 is less than k, which was the first condition says that size of S1 is greater than equal to k. So it is 2, k is equal to 3, so this condition fails. Now the second condition is true. The size of k is equal, greater than or equal to S1 plus S3. So S1 plus S3 comes out to be 3, and the second condition also says that the size of this is greater than or equal to 3. So we return the mid value, that is 7, and this comes out to be the solution for this particular number. So this is how we apply the median search algorithm in order to find out the kth best, or the kth, you can see we had to find out the fourth median, and here you can see from this particular data that we have 1, 2. So if we sort this particular element, it comes 7 comes out to be the fourth median for this particular data. So if we sort, let's say 3, 4, 6, and then comes out to be 7. So this is the seventh smallest element, or sorry, the fourth median of this particular array. So if you just sort and see, this is simple way to verify whether the answer that you are getting from here is correct or not. You can simply sort the array and see what is the median value and which result you should get, and from this verification you can make out that the algorithm is working correctly or not. So this is the recursive implementation of the median search algorithm, and here you can see we start from the main function. The same data has been taken over here. So what do we do? So we are call int element is equal to median of array 0 n minus 1 to k. So we are passing out these elements and calling this particular function of median search, and then here you can see we are just following all those steps only that we did in the previous example only. We start with the loop till the length of that particular array, and if a of I is less than the index value, we simply assign this particular value and move ahead. Else, if ai is equal to a of index, so s1 of j is equal to ai, s2 and s3, and this process of doing this particular task is repeating, and if the value of j is greater than equal to k, median is equal to s1 0 j minus 1 k. And here you see you just apply this algorithm and on the data that we have given, and just see whether you are able to get the result or not. So this is basically the recursive implementation of the median search, where we are calling the median function again and again, as we did in this particular previous example that we have done. So the complexity analysis of the median search. So in the best case, condition 2 is met in the first call to median search. So no further recursive calls are made. Is condition 2 in the condition 2, that means what does it say? The length of s1 plus s2 is greater than equal to this. So we finally return what is the random number that was generated. So that is the output. So if the condition 2 is met in the very first call, that means this is the best case, this is the minimum time we are able to spend for the algorithm will take in order to find out the element that we are searching for. So it comes out to be O of n. Now, in the worst case, condition 1 or condition 3 are met. So, in both the cases, we are making recursive calls to the function itself. So, in that case, you can say the recursive call will be made only either to subpart 1 or subpart 3. You can say the subsequence S1 or subsequence S3. But it is possible that the subpart S1 or S3 contain n minus 1 elements. So you can say it can be any number. There is a possibility because in the subsequences we are not aware how many elements are there, because now you see this is a different kind of recursive relations. Here the element data is, the array is not divided into half. The array is divided into any kind of subsequences. So we just assume over here that the any of these subsequences may contain n minus 1 elements. If it contains n minus 1 elements, then its recurrence relation is of the form of Tn is equal to Tn minus 1 plus n, and we have already solved this kind of recursive relation while studying about the asymptotic analysis, and on solving we see that T of n is equal to On square. So that means for the median search, in the best case, its time complexity is of the order of n, and in the worst case, its time complexity is of the order of n square.